Okay, students, welcome to part 2 of our equilibrium journey here on YouTube. It's Dr. Mullins, your host. So let's look at this problem here real quickly. We've got nitrogen dioxide, a gas, dimerizing, so 2 molecules of nitrogen dioxide forming 1 molecule of dinitrogen tetroxide as a gas. If we initially have 1 atmosphere of NO2 introduced into a flask, doesn't really matter right now what size the flask is, at a temperature, which is unknown but irrelevant here at the moment, where our Kc value is 3.33. We're going to ask 2 questions to try to answer them. First, what is the partial pressure of N2O4 at equilibrium? Well, we're also going to find out, obviously, what the partial pressure of NO2 is at equilibrium. And that'll help us answer the last question, what is the total pressure in the flask at equilibrium? So let's pause. We're going to go and fill in our ice table and begin to look at this. Okay, people, I've set up the equilibrium reaction, shown here again, and an ice table, and we've put in that we have 1 atmosphere of NO2 to begin with and 0 of N2O4 in this case. And then our change, obviously based on the stoichiometry here, mistake there. We should gain plus x, not plus 2x, so I'll have to fix that on the right-hand column there. We're going to lose 2x and change for NO2. We're going to gain plus x for the N2O4. So that we're going to have 1 minus 2x and x for our equilibrium concentrations. And then we're going to go ahead and we're going to put that into a Kp expression here in just a moment. Okay, now you can see I fixed that. And I've got my Kp because we have partial pressures here. Kp for this is the partial pressure of N2O4 over the partial pressure of NO2 squared. So if we take our ice table information and fill that in now, we've got Kp equals x over 1 minus 2x squared. So we see here, we're going to, very simple, we're going to get a quadratic we're going to have to solve for. But we're not done yet, because remember, we were given Kc in the problem. So we need to go back and we need to look at and consider the relationship between Kc and Kp, considering the number of moles of gas, the change in number of moles of gas. So the change in number of moles of gas here, we've got 1 mole of product gas and 2 moles of reactant gas. So our delta N here should be 1 minus 2, or negative 1. So we're going to use that in our relationship. We're going to set that up for Kp and Kc so we can plug Kc into Kp and solve this problem. Okay, coming back. Now remember, I told you delta N should be negative 1. We have the expression Kp equals Kc times RT raised to the delta N. So we weren't given a temperature here, which is a problem. Okay, so let's just assume for today that since we're not given a temperature in the problem, let's use 25 degrees C, or 298 Kelvin. Now, if this were an exam question, I would give you a temperature. Okay? Poorly written problem here. Let's use 298. And so now we can solve for Kp. We can figure out what the equilibrium constant is in terms of partial pressure simply by plugging in 3.33 times the factor of 0.0826 liters times atmosphere over moles times Kelvin times our temperature 298 Kelvin raised to negative 1, right? And we can solve for that. And let's do that. And then we're going to take that and we're going to solve for x using this part here. So I'm going to skip to writing out all that here in just a moment. Okay, catching back up. So if I solve for that Kp, I get approximately 0.1362. And now I can pull back down that x expression here from the law of mass action, and I get 0.1362, our Kp value, equals x over 1 minus 2x squared. Now, I cannot simplify like I did in the previous example. I don't have squares for everything, so I can't take the square root of everything. To make it simpler, I'm going to have to FOIL the denominator here on the right, get things into x, rearrange things by multiplication and division, and I'm going to end up with a quadratic. I can see that I'm going to end up with a quadratic. Alright, so let's do that. Okay, coming back to this now. So if we FOIL here, we end up with now this factor of 0.1362 equals x over 1 minus 4x plus 4x squared by multiplying using FOIL, which you should remember. So, if we multiply both sides by the denominator then, right, now we get this thing where x equals all this other stuff. If we want to subtract x from both sides, it becomes, here in red, and I've rearranged things to put x squared first, we've got 0.5447 rounded times x squared minus 1.5547x plus 0.1362 equals 0. So we've got our quadratic. Yay! You know, you're thinking that. So we've got our a, b, and c. We could use the quadratic formula and solve for this. And solve for x, which then is our equilibrium partial pressure for N2O4. Now, there might be a simpler way without having to use quadratic. Let's think about this for a moment. What is our value for Kp? It is rather small. It's less than 1. Okay, so Kp is small. We might be able to assume, though, that x is relatively small. If x is small, right, then our equilibrium here in terms of the change there, 2x might be small, right? And we might be able to plug in and simplify this using that approximation that x is small. So let's try that for a moment. We can always come back and do the quadratic. So let's try that. Okay, so let's do our approximation. If x is small, it means it's much, much smaller than 1, which was our initial concentration there. So if that's the case, we can assume that equilibrium concentration for our initial sake is approximately 1. Right? If that was the case, and we plug that in, x over 1 squared, we get x solving to be 0.1362. However, now we need to check to make sure our approximation. If we take that over the initial concentration of 1 and multiply by 100, we get 13.62%, which is much higher than 5%, which is what we need to be 5% or less for our approximation to be valid. So, this works sometimes. This works and you get a value where x is small, right, that checking the approximation, and then you can use that x and all that. We can't here because x is not small, so we have to go back and we'll have to solve using the quadratic formula, right? So, I'm going to end here and encourage you to try to work through this problem just as I have and then apply the quadratic formula, right? So do that before Monday if at all possible. And then maybe we can resume this problem, put the finishing touches on it on Monday, as well as working through another example or two. So I wanted to encourage you to look at the examples in the book, look at my examples, look at Khan Academy, become very comfortable with equilibrium and ice problems. This will take some practice. It will probably take some time coming to my office, but I know each one of you can do it. So I'm confident in you. We just got to put in the time. All right. Good luck, and I'll see you soon.